Welcome back to our statics video in which we were looking at a friction problem. This is an example problem from chapter 6 in the textbook where we have a box on an inclined plane. So we're right in the middle of this problem and we're about to calculate the friction force, which is 476, I'll round that off to 476 newtons is the friction force. So just a quick recap here. We have this box. It's on an inclined plane at 30 degrees. Its mass is 140, which means its weight in terms of newtons is 1373. Now, the way I like to think about approaching these problems is set it up with the weight going straight down, and then rotate the whole thing. If this is on your piece of paper, just rotate your paper. Rotate it so that the surface of the ramp becomes horizontal. So if the ramp was initially at 30 degrees, in order to get it horizontal, you had to rotate it 30 degrees. Okay, and which means that weight that was going straight down is now making a 30-degree angle, but that 30-degree angle is with respect to vertical, and we want to use the angle with respect to horizontal, which is 60 degrees. So we use that 60 degrees to find the x and y components of the weight. The weight is both pressing up against the ramp, which causes a normal force, which causes friction, but it also, there's a component to the weight parallel to the surface of the ramp, which is going to have a tendency to make it slide down the ramp. So in part A of this question, we want to know how much force do we need to apply in the upward direction, parallel to the surface of the ramp, to push this box up the ramp. And what we need to do is we need to overcome the weight in the x direction. And since we want to push it up the ramp, since we want the motion to be going this way, up the ramp, that means that the friction force is going to be going in the opposite direction. So friction is, the direction that the friction force takes is always opposite the motion. So since in part A of the question we're talking about pushing the box up the ramp, that means the friction force is going down the ramp. Now when we look at it going the other way, when we look at the box potentially sliding down the ramp, friction will be working in the opposite direction. So you have to keep that in mind. The direction of the friction force can change depending on the direction of the motion. In this particular part of the question, though, we're talking about pushing it up the ramp. So the friction force is going to the left. So if we want to sum the forces in the x direction, we know that they will equal 0. What are those forces? Well, we have the x component of the weight. That's going down the ramp. That's going to the left. We also have the friction force, which again is going to the left. And then we have the force P that we're going to be pushing with that's going to go up the ramp. We want to know how much P do we need, how much applied force P, how much of a pushing force do we need so that this all cancels out. So it's the point at which motion is impending. It's the force at which if we apply just a little bit more than that, the box will actually start to move. And so if we solve this for P, we just get P is equal to Wx plus F. And we already have these values calculated. The x component of the weight was 687. The friction force we just calculated to be 476. And so the force that we would have to push with in order to make it slide up the ramp is 1163 newtons is how much we have to push against the box in order to make it slide up the ramp. Now let's take a look at part B of the question, which asks us how much force do we need to apply to push it down the ramp. So there's a couple key things here. One is, do we have to push it at all? Maybe it's going to slide down all on its own. The other thing we have to keep in mind is because the motion now is going to be going down the ramp, the direction of the friction force changes. It flips. Friction is always going the opposite way. It's always opposing motion. So if we're talking about pushing the box up the ramp, friction goes down. If we're talking about pushing the box down the ramp, friction goes up. So we can sum the forces in the x direction, and it will equal 0. Before we do that, let's just take a look at the Wx, the component of the weight in the horizontal direction, minus the friction force. Let's see if we do nothing, if we don't push against it at all, what is going to happen. So this diagram is taken from the textbook. The author here, instead of using the angle with respect to horizontal, remember this, if I continue this line here, this is 30 degrees, and this angle with respect to the horizontal is 60 degrees. I always prefer to use this angle, the 60-degree angle, which means that the vertical component is found using sine. So this is like Wy. Well, actually, no, this is Wy is equal to this. So Wy is equal to the weight times sine of 60. And Wx, the x component of the weight, is equal to the total weight times cosine of 60. Now you can see here that the author just used the 30-degree angle, but then switched sine and cosine. I think that can get to be confusing, which is why I always like to do it the same way. I always recommend using the angle with respect to horizontal, and that way the vertical component is always sine, and the horizontal component is always cosine. So we already found the x component of the weight in the part A of the problem. That x component of the weight was 687. And the friction force is going to remain the same. It's still the same weight in the y direction, and same coefficient of friction. So the friction force is still 476. The only thing that's changed about it is the direction. Now we can see right here that the horizontal component of the weight is actually greater than the friction. So the friction force is not going to be strong enough on its own to prevent the box from sliding down the ramp. So we can see already that that we're not going to have to push at all in order to get it to go down the ramp. In fact, what this means is we're going to have to still be pushing up against the box in the upward direction. So the Wx component was 687. The friction force that's going to try to stop it from sliding down the ramp was 476. And so that difference is 211 newtons. So if we did nothing, if we just stood out of the way and didn't push against this box at all, it would have an imbalance of forces. It would have 211 newtons in the downhill direction. So this box is going to start sliding. Okay, so in order to prevent it from sliding, let's say that we want to just gently ease this down the ramp. So we want that force to be just enough to keep it from moving, so that if we reduce our force at all, the box will slide on its own. We can find what that force is. So the force to push it down the ramp is not really a downward direction force to push it down the ramp. It's really more of an upward force to prevent it from sliding down the ramp. So we could use our equilibrium equation here to say that we want the sum of the forces in the x direction to equal 0, which is going to be that x component of the weight minus the friction, also minus the pushing force. And I know that our plus and minus signs seem a little bit opposite, but that's because we're talking about going down the hill. So I guess we could, maybe if that's too confusing, let's change that to be negative Wx going to the left, positive friction going up the ramp, and positive pushing force also going up the ramp. And so we've already found, well, I'll just write in all the values, I guess, 687 and negative 687 plus 476 plus P, and so P is going to equal 211 newtons. So we actually have to push up the ramp to prevent it from sliding on its own. So if we wanted to gently ease this box down the ramp, we would apply 211 newtons of force and then just slightly ease off on that force. Maybe take it down to 210 newtons, and the box would begin to slide. So how we answer this question really depends on how it's worded. If the question just says simply what force is required such that downward motion is impending, then we have to apply the 211 Newton force. If the question is worded to just simply say what force is required to cause the box to slide down the ramp, well, I guess the answer then would be 0. We don't have to do anything. We just have to get out of the way, and gravity will take care of that for us. So I think I'm going to stop this video right here. We still have a few minutes left, but I don't like being interrupted in the middle of an example problem, and we still have part C to do. I'd like to be able to get through all that uninterrupted. So we'll stop here and do part C in the next video.